Hi, my name is Jim, and this morning we're going to be talking about another type of power supply which is very popular. It's called a full wave rectifier, specifically the bridge wiring orientation. So we'll talk about both full waves and bridges. Now, to see the advantage of this, we're going to start with the positive half wave power supply that we spoke to the other week. And we saw that the output uses the positive going peaks, and this can also be negative going. It depends upon what you want, what you need. And we saw that the ripple component was a discharge of capacitor from the peak into the next charging peak coming out of the rectifier diode. And we ended up with a peak-to-peak ripple, which was pretty significant in this particular case, of a peak-to-peak right in here. Now, we also talked about making the capacitor larger to reduce this. There are limits on that. And reducing the load, meaning the lower current flow, would also reduce the ripple. But wouldn't it be nice if we could take the negative going part of this power supply, which we're basically not using, because the diode is, excuse the language, cutting off the bottom. It's reversed bias down here, so none of this gets through, and on the quadrants 1 and 2 it is forward biased, which hence allows it to charge the capacitor. Now we can flip this guy over. We're going to do ourselves a lot of good, and the way that would look is we would have a pulse in between like this. That's not too bad. And instead of having the capacitor discharge down to this point, it would discharge down to this point and then recharge again. So as you can see, if we're going to be recharging our filter capacitor twice as often, is that the ripple is going to be basically reduced a lot depending upon these two components being the same. So the question is how do we do that, and what's it going to cost us, because, well, nothing's free. So we're going to get into a bridge rectifier. I've drawn it down here, and you see that it has 4 diodes in it. And the advantages of a bridge rectifier is it's easier to filter, or the filter capacitor can be a lower, I shouldn't say voltage here, what I mean is size, for the same amount of peak-to-peak ripple. The disadvantages of it is it needs 4 diodes, and fortunately in these days diodes are cheap. Back in vacuum tube days they were very expensive, so bridge rectifiers weren't at all popular. And the other disadvantage is we're going to have 2 diodes conducting at the same time, which means that we're going to have about, using our level 1 model, 1.4 volts lost as the voltage drop across the diodes. That may or may not be the case. So here's a picture of a bridge rectifier, and this could be a commercial power source like a wall outlet, or it could be the secondary of a transformer. Doesn't really matter. And I didn't show any grounds in here, and I need to do that. So here we have the load, and typically if we're going to be troubleshooting, measuring something, what we'd want to do is measure across the load, so I'll put the ground here. Now what I see a lot of students do is they have some grounds of equipment like a scope probe here and other grounds up here, and when you do that, the ground itself shorts out a diode someplace. Remember that a scope BNC's alligator clip connects to the chassis, connects to the green wire and the power cord that goes into the common ground, and so does other equipment, so you can actually get a short through the ground clip of your test equipment if you're not careful. So once you decide what the ground is, make sure all of your test equipment references that ground. Likewise, if I wanted a negative output, all I'd have to do, and getting rid of that for a minute, would be to put the ground here. So this is going to be common, and now our output, which would be this point, would be negative. So we can establish positive or negative any way we want to, depending upon the ground, but what is important is we need to have one and only one ground point, and this is not a good point to make for a ground. analyze a bridge rectifier, I mean, it looks pretty intimidating. You got 4 diodes in there, and you know which ones conduct, which ones don't. So I kind of simplified things a little bit, and this is the way I figure things out, is I let the positive quadrants 1 and 2 of the sine wave be a positive battery. And then when I look at it, is what I see is only 2 diodes are in fact in the circuit. Positive current, or conventional current, flows through the anode of this, which we would expect, because the anode has to be positive with the cathode. And note that I've said that many times throughout the course of all of this. Flows through the load resistor and charges the filter and so on and so forth. Then it flows back through the other diode into the negative terminal of the battery. So in this case, when we're in quadrants 1 and 2, only these 2 diodes are conducting. Now, in the sine wave, of course, we have quadrants 3 and 4, and I have indicated that by flipping the battery around. Now, conventional current flows out of the positive terminal of the battery through this diode, up in this direction, across the load. Notice the plus and minus drop just as before, back around and up through this diode to get back to the negative terminal of the battery. So for quadrants 3 and 4, when the input waveform is negative, these 2 diodes conduct. And I am assuming here, by the way, I forgot to draw this, that this is going to be a ground, and we're interested in a positive output voltage. So what we have here is a toggling back and forth of the 2 diodes. These 2 conduct 50% of the time here, and these 2 conduct 50% of the time here. And when these are conducting, these 2 are reverse biased. They're essentially off. Diode's kind of like a voltage control switch. Contrary, when these are conducting, these are reverse biased, so it's kind of like they're not there. So in this way, we get a waveform which is much easier to filter. And one of the things that I need to point out, I didn't put it down here, but I will, is that the ripple factor and percent of regulation equations are the same as for a half wave, so it does not matter. Now, what is a little bit different is the frequency of the ripple equals 2 times the frequency of, I'm going to call it the input voltage, maybe I'll just write down SRC. And that is because you're getting 2 pulses per cycle of input out of it. So if I have a 60 hertz supply feeding a bridge, what I'm going to get out of that is 120 hertz ripple, and as you can see by the higher frequency, it's in fact easier to filter. Now we can go backward on this. If you're told that, say, the ripple frequency is 120 hertz, and you have to be told if it's half wave or a full wave rectifier, then all you do is divide this by 2 and you end up with your source frequency. In a half wave circuit, the ripple frequency is the source frequency. Now your book speaks to, and I'm not going to mention the name of the book, they hardly mention bridges at all, which kind of bothers me a bit, but they have another type of full wave rectifier. By full wave I mean that we're taking advantage of the negative part of the sine wave, meaning this guy, to make the filtering easier, and that uses a center tap transformer. Now, once upon a time, back in the vacuum tube days, winding the additional turns on a transformer was cheaper than installing a second vacuum tube. But as time went on and the bridges became more popular because of low cost of a bridge rectifier, the full wave center tap transformer approach was found to be in disfavor. Now it works very easily. If I have, for example here, 20 volt center tapped, what that means is, and we're just going to be talking about peak here, so I don't confuse everybody with the RMS stuff. So we'll just let this be peak. That means that there's going to be 10 volts peak here, and 10 volts peak here, and as you can see by the windings, is that these are going to be series 80. So the voltage from here to here is going to be 20 volts. Now what's important is that the wiring on this is non-critical. In older radios that I repair, these two will typically be yellow, and this will be yellow and green. The way you wire it doesn't matter. This is black, no polarity. Who cares? You know, in some transformers you very much care, but not this one. So if we look at this and assign polarities here, what we're going to see, here's a different color here, is the top of this winding is going to be plus and minus, and what we're looking at is this point right here. So what we see is relative to ground is that this side is positive, which forward bias this diode, current flows through it, charges the capacitor, goes through the load, and so forth, returns through the center tap and makes a path like that. Now on the negative half cycle, the polarities shift, and again I'm simply looking at this point to make it a little bit easier, and instead of this being positive, it's going to be negative, and this is going to be positive, and this is going to be negative, and this is going to be positive. And again, note that we're series 8ing on the secondary. Now, relative to ground, which is the center tap, the anode of this diode is now positive. Conventional current flows in this path up and through, charging the filter capacitor and also feeding load resistor as before. And the return path now is up through the center transformer into the lower component of the winding. So in a full wave rectifier, you've got the additional cost of winding on a transformer as one of the downsides, and that's a significant downside. The transformer has to be larger, of course. You're down to 2 diodes. That helps. Only one of them is conducting at a time, which means that the total loss of the diode is going to be 0.7 volts approximately. And these two are going to toggle back and forth relative to which one's going to be conducting. As the case of the bridge, F rip is going to be equal to 2 times F input. So again, this is easier to filter like the bridge. It's full wave. It has basically the operation of a bridge, except it requires a more expensive transformer and 2 less diodes. So that's the other, can't say common anymore because it was of yesteryear when diodes were really expensive, type of circuit that offers full wave, easy to filter outputs. And the bridge is the standard bearer. I blew up a wall supply. I don't remember how I did it, but I took it apart and mounted on a circuit board. Inside this 12-volt DC wall supply were 4 diodes in an integrated capacitor. So that's kind of interesting. And the other one thing I wanted to mention here, and I've seen this here cause students a lot of pain, is they build a bridge rectifier, and what they end up doing is, for the source, they plug it into a wall supply rather, AC, and then they expect their bridge rectifier to work and provide DC for some sophisticated electronics, for example, in the biomedical project lab. You know, there's a lot of cool circuits in that, and the whole thing depends upon the power supply working. Now, students make a wiring error or get the cap in backward or whatever. I mean, I do it. So what? You fix it and move on. But in the meantime, what happens is that they have a transformer here, and it's a 24-volt secondary, and they end up burning it out. So what's recently been added is what's called a polyfuse. It's a resettable fuse. Symbol looks like an S without the line through it. And when this gets hot, it opens the circuit. So that offers a degree of protection. But when you're building this, seeing that any polarity will produce the correct output, you can use a DC power supply and just set the current limit for 50 milliamperes. So if you have a short downstream, the voltage of the supply will drop until the current's 50 milliamperes, and usually that drops to, say, less than a volt. What that means is that any short circuits you have downstream for example, if I had this cap in reverse and it was starting to break down, is that I see it over current. I see that the voltage on the power supply goes to 0, and it also lights a CC LED called constant current LED, and I have time to flip the switch. Something's wrong, and I didn't blow up the cap. So if you're using bridge rectifiers, and you can, remember current limited DC sources. The DC supplies at the school are current limit. I've got one on the bench at Temna, and I tried to blow it up many times, and the closest I came was trying to charge a lawnmower battery, lead acid, and got the leads mixed up. Fortunately, it had a reverse protection diode in it, a 3 ampere guy, and it failed short. And when I noticed that the leads going to the battery were starting to melt, I figured out there was something wrong. The good news is I only had to replace a $1.50 part in that power supply, which cost $150. So whoever designed that was a very, very forward-thinking engineer, very conservative, and that's a good thing. So this will conclude their little lecture here on bridge rectifiers. We'll be using this in the industrial project, so you'll have the fun of wiring these. Now, wiring them in bridge format, like that, isn't necessary. You can take these 2 diodes, for example, and lay them down like this. This will go to this guy, and this will go to this guy, and tie these together, and do the same thing with the other diodes, only reversed, and you're all set. If you want to simulate this in a simulation software package, typically they won't allow you to run 45 degrees. So you're going to have to think about that, run them either vertically or horizontally, but if you get it wired right, well, who cares? So that'll conclude our little talk today on bridge rectifiers, and thank you for listening.